Well, thank you very much. Can you hear me? Are all these things on? Well, something interesting happened to me today, which was that I attended my first meeting of the House of Lords Science and Technology Committee. When I was appointed to the House of Lords, I estimated it'd be 15 years before they put me onto that committee, and I was 1 year out. You know. This lecture is about Dickens and science, and I shall start really with the common view. Like others, when I first read Charles Dickens' novels, David Copperfield, The Pickwick Papers, Great Expectations and Hard Times, I was so bowled over by their great characters and their adventures in their vividly described Victorian milieu of schools and business and law and crime, and on the beach at Yarmouth or in London's foggy streets. And everyone who reads Dickens has their own reactions and maybe learns different lessons. I laughed a lot, to the annoyance of my wife, as I took many weeks slowly reading Dombey and Sons amid the changing scenes of North London and the arrival of the railways. And my cautious approach to finance has probably benefited from Mr. Micawber's advice that if one's income only just exceeds expenditure, that leads to happiness, but if otherwise, then misery. But I did not think then that I was reading novels written by someone with a deep appreciation of science and its wider intellectual and cultural connections. Furthermore, as I shall argue, Dickens had original and important ideas about how science develops, which he illustrated in his writing about the roles of scientists and their lives. We should remember that the word scientist was only introduced by William Whewell in 1833. Whewell was a historian and philosopher of science from Master of Trinity College, Cambridge, who was also well known for inventing some important terms in physics, such as the anode and cathode, in his conversations and correspondence with Faraday. Whewell said, we need, quote, "we need very much a name to describe a cultivator of science in general." The quote continues, "I should incline to call a physicist or chemist as a scientist, just like an artist is a musician or painter, etc. Up until then, scientists were often called philosophers. One of my passions is Fitzroy and Darwin, having been head of the Met Office and seen a picture of Fitzroy every day on the wall at the Met Office where I worked. As Captain Fitzroy called Charles Darwin when they were on their 5-year voyage of HMS Beagle, he called him Philo, as an abbreviation of philosopher. Like most readers, I generally thought of Dickens as being highly critical of the social and environmental consequences of the scientific and industrial revolutions of the 19th century. This was the moral aspect of his novels that the literary critic F.R. Leavis, a great Cambridge a character of the years when I was a student, which is what Leavis so much admired. He did not seem to me at that time connected to science. Dickens' morality was practical, as he described and campaigned about the dangers and ill health caused by the polluted atmosphere and rivers in his novels, such as in Little Dorrit. He wrote about slimy gaps and causeways winding among old wooden piles, and rags of handbills offering rewards for drowned men, the sort of usual gloomy scene. But he campaigned in his magazine, which a strong feature of Dickens' writing, which many people are not aware of, and certainly I wasn't. In one of his magazines was Household Words, and there was another one later. And in his magazine Household Words, he campaigned about London's great stink, which was so bad, as you probably remember, in 1858, that Parliament had to stop. And only within a year, Parliament introduced legislation in 1859. But Dickens was campaigning very strongly during this period in his magazine, and he, with a colleague, wrote a well-known article on a way to clean rivers. So things happened quickly then. You had a big stink, you had articles in the newspaper. 1859, you had legislation, and Joseph Bazalgette was off on his way with practical schemes. Nowadays, of course, people remember Dickens's writings about the environment and about the rivers, but they generally refer to Dickensian as simply a term of environmental frightfulness, not as a reference to a man who really tried to understand and deal with environmental and social problems. There needs to be a little education on this to the Green Party, because for recently the well-meaning but perhaps misguided remarks of the leader of the Green Party in the House of Commons referred to Dickensian environment. Well, of course, that was the point I'm making. This article, by the way, this report was reported in The Guardian too, which doesn't always report parliamentary proceedings. I'd now like to move on to my reassessment. So my view of Dickens' interest in science changed completely when I bought a copy at Gatwick Airport on a trip to Cuba. I read his last novel, Our Mutual Friend, published in 1865. Remember, his early novels were in the 1830s, so this was 30 years on. And this novel revealed his considerable knowledge of the great developments in science in the 1850s, 1860s, and how these had become part of ordinary people's understanding of the world around them. Although this point seems to have been missed by most of Dickens' writing as well as his biographers, as I shall come to at the end, Peter Ackroyd's novel, biography of Dickens, does refer to some aspects. I learnt from my son-in-law, Professor Giles Foden of UEA, about the importance of understanding Dickens by looking at these published magazines, which he wrote with many other colleagues. One was Household Words, and the other one was All the Year Round. And in fact, he'd been writing in these magazines throughout his writing time. These publications were approved of, for example, by the Morning Chronicle as a very good two-pennyworth, covering current affairs from politics to railways and even science policy. Many of his novels, as not everyone remembers these days, were written as chapters publicized in these periodicals. And so as each chapter came on, this was great excitement. And for example, the famous occasion when one of the big steam packets arrived in New York, and people went down to the harbour in New York and shouted up what had happened to the latest stage in Little Dorrit. Dickens expressed his general ideas about how new fields of science emerge in his very profound and almost totally ignored essay called History of a Young Ology. So this period of the 19th century, you had lots of ologies: meteorology, geology, archaeology, and so on. And he published this essay, which is well worth reading, in All the Year Round in Volume 6, 1861, pages 186 to 190. And this was his term for the new sciences of the past 2 centuries, notably of geology and ethnology, which were formerly departments of natural history. And as I've mentioned, meteorology, archaeology are other examples. The first of his 3 points was that in the early years of an ology, there may be a vast, to quote, a vast multitude of results that might not be very accurate or very interesting. But this is the stage, of course, when theories begin to emerge. He also recognized that individuals are important, especially at this stage, as in his attribution of progress in the new science of meteorology to Dr. Dalton of Manchester. As he commented, Dr. Dalton is mostly well known, and probably to this audience here today, for his great work on the establishment of atomic theory, the great scientist of Manchester. Dickens approved of Dalton's early advocacy of popular engagement to advance natural sciences, which of course is so much easier today with widely available and low-cost instruments, computers and communication. And the Royal Meteorological Society, I'm very pleased today in the audience, one or two of my colleagues from the Met Office, the Meteorological Society now very much carries on this Dickensian, Daltonian view about science. Dickens' second point is that no accurate science is popular until people have begun to generalize from the facts. He talks in some considerable detail about the developments in meteorology and why people began to believe meteorology with the use of telegraph and signals. Of course, in Parliament, people still don't believe in meteorology, but that's another matter. But he made this very interesting point that the wider and more inclusive the generalizations, the more interest do they possess. He illustrated this idea in the field of meteorology as it developed connections with other sciences such as aurora, magnetism, and thermodynamics. But it was only 50 years later that this very profound idea was taken up and worked out to a greater extent by Henri Poincaré, the famous French mathematician and astronomer. Poincaré explained in his famous book, Science and Method, 1905, in which he explained how success in mathematical research is not only when a lengthy calculation, this is a quote, a lengthy calculation leads us to a simple and striking result. No, you should do more than that. We're not really satisfied until we have shown that we might have foreseen the calculation before we'd started, if only we'd had the intuition. And this is the challenge of doing research, as it were, to end up with something that you feel intuitively must be right, and which he described as its most characteristic features. And one of the further reasons for this, it enables research to continue. It's the best method of progressing research. But most importantly, this semi-intuitive result might be adapted to other problems of a similar nature in other sciences, preferably using simple arguments summarized in a few lines. When I showed Poincaré's book to my professor, George Batchelor in Cambridge, he said, he was astonished, he'd never heard about this book. He said, this should be the aim of all of us in applied mathematics. Of course, hard science has to be done before the fog of research clears and the new ideas emerge. To, as it were, also relate, as you can see, this is beginning to sort of touch on the sort of almost the philosophical, the sensuous aspects of science. And this is exemplified in the beautiful passage in George Eliot's novel, Middlemarch, which I read as a student and was very moved by this idea of a scientist. And George Eliot described the pleasure scientists experience in thinking about the wider connections about their particular discoveries. In the novel, the hero, Dr. Lydgate, quote, stretched his legs in the agreeable afterglow of excitement when thought lapses from examination of a specific object into a suffusive sense of its connections with all the rest of our existence. Lydgate, who, by the way, also had problems of falling in love with ladies, but which is a topic, I thought I couldn't resist that this week. Lydgate felt a triumphant delight in his studies and something like pity for those less lucky men who were not of his profession. So that was 1874, but in the same period. The leaders of science today perhaps could be more encouraging about this approach to explaining and progressing research, even if they still cannot agree on whether and how best to encourage new ologies. But they generally agree with Dickens and Poincaré's views about the value of explaining science to the wider public and of making connections between the different branches of science. Now, Dickens made use of these broad ideas in his novels, and he was surreptitiously popularizing science thereby, as he wove the latest observations and even theories into the plots of his very human and apparently unscientific novels. In at least one case, like other writers have also done, by generalizing certain ideas then current, he even proposed an important scientific concept before it had been considered in the scientific literature, as I shall explain shortly. Dickens wrote with some satire and praise about scientists. He often poked fun at them and also those who believed in science, which of course is still with us today. But no more than he did in all his books with respect to every professional and business character, and also his much ridiculing, of course, of business practice and legal practice. In Hard Times, written in 1851, that's 15 years earlier, he ridiculed the standard schoolmasterly view of science as being a matter of stick to facts, rout out everything else, Mr. Gradgrind's dictum. He also mocked the amateur scientists who met at the Pickwick Club, driven ostensibly by pure curiosity, in order to consider, quote, speculations on the source of the Hampstead ponds with some observations on the theory of tittlebats. A really good scientific meeting in my view. So this was a gentle satire on the British Association for the Advancement of Science, which was set up in 1836 to popularise science and its applications. In a way, Dickens was taking both sides of the 19th century philosophical debate, recently reviewed in a fascinating biography by Richard Reeves of John Stuart Mill. And this debate was between Mill and Whewell about whether science was simply to be judged by its utilitarian and numerical effectiveness, which is Mill's position, or, as Whewell, who surprisingly was also very emphasized the intuitional value of science for providing inspiration and understanding. In Our Mutual Friend, the gloomy wine waiter who at a dinner party pours out a dodgy Chablis, apparently a common problem then, he is compared to an analytical chemist saying under his breath, "You wouldn't drink this if you knew what it's made of." In Dickens, any scientist in the city was also highly suspect. Some of those forming dubious companies like Collapse, Vortex, Docket and Company. I feel rather close to that, having set up a company that deals in vortices myself. But so he obviously had modern fluid dynamicists in mind. But when it came to individual scientists, Dickens wrote admiringly about them in his essays, particularly those whose work he used in his novels. John Dalton of Manchester was famous for his discoveries in chemistry and also wrote on meteorology. Dickens reviewed the latter in one of his essays, and meteorology then appeared in Oliver Twist, in the wintry scenes of snow blown about in particular patterns of wind. Dickens also learned of the fearsome ocean waves experienced by the transatlantic travellers, which he wrote about in Martin Chuzzlewit, and he quoted the work of the pioneer American Navy oceanographer and meteorologist Lieutenant Maury, who indeed greatly influenced Fitzroy here in England. He described the waves as countless miles of angry space rolling on the long heaving billows, a boiling heap of rushing water, mad return of wave on wave, ending in a spouting up of foam that whitens the black night, incessant change of place and form and hue, louder howls the wind and the wild cry goes forth upon the storm, "A ship!" The science in Dickens' novels usually connects nature with people and animals. In the opening page of Bleak House, one reads a naturalist's notebook transformed into art. Fog everywhere, fog up the river where it flows among green, is a word most people don't know, an eight, which is an eyot, but amongst the green eyots on the Thames and meadows. Fog down the river where it rolls, defiled among the tears of shipping and the waterside pollution of a great and dirty city. Some people think the same today. But fog creeping into the cabooses of collier brigs, fog in the eyes and throats of ancient Greenwich pensioners, wheezing by the firesides of their wards, fog in the stem and bowl of the afternoon pipe of the wrathful skipper down in his close cabin, fog cruelly pinching the toes and fingers of his shivering little prentice boy on deck. Chance people on the bridges peeping over the parapets into a nether sky of fog, as if they were up in a balloon hanging in the misty clouds. Dalton had been in a balloon. One is reminded of Oscar Wilde writing in 1889 that only artists enable people to see fogs, not because they are fogs, but because poets and painters have taught them the mysterious loveliness of such effects. There may have been fogs for centuries in London, but they did not exist till art had invented them. That's Oscar Wilde. But no Oscar Wilde could have conjured up the extraordinary geological perspective that Dickens used in the same passage in Bleak House to deepen the mysterious gloom of the London scene. As much mud in the street as if the waters had but newly retired from the face of the earth, geology. And it would not be wonderful to meet a megalosaurus, 40 feet long or so, waddling like an elephantine lizard up Holborn Hill, smoke lowering down from chimney pots, making a soft black drizzle with flakes of soot in it as big as fully grown snowflakes. Gone into mourning, one might imagine, for death or the sun. For death of the sun. This passage reflected the great interest in the dinosaur period of geology and the discoveries of parts of huge skeletons all over Europe. Scientific societies had generated considerable excitement and publicity, which is why such a remarkable a reference appears on page 1 of a popular novel. Dickens' last novel, Our Mutual Friend, which I've referred to already, touches on a range of science. It was written after the huge publishing success of Darwin's Origin of Species, which ran out on the first day it was published, many tens of thousands bought, which had created so much popular and scientific interest in every aspect of the early history of Homo sapiens and the origins of every other animal and plant species, and of course much geology as well. Part of the reason for its immediate interest was because the book built on the geological developments as well as the studies of existing species. Like Dickens, Charles Darwin himself was interested in many of the public scientific issues at that time, considerably outside biology and geology. At the same time, in the 1850s and 1860s, there were also great developments in classical physics and mathematics across Europe, which raised huge public issues and debate, with scientists like William Thomson, later Lord Kelvin, and Sir George Stokes, both mathematicians taking a prominent public role. The most dramatic scenes in Our Mutual Friend is about our poor family living in the East End of London alongside the polluted Thames and in a darkening and equally polluted atmosphere. Dickens refers to a then current apocalyptic explanation of the darkening as being caused by the fading strength of the sun. Quote, while the sun itself, when it was for a few moments dimly indicated through circling eddies of fog, showed as if it had gone out and were collapsing flat and cold. Several literary studies have suggested that this passage refers to the recent scientific studies by William Thomson, following the earlier 18th century analysis by Pierre-Simon Laplace in Paris, which concluded that the sun's power would gradually run down, and even more profoundly because of the heat death of the universe associated with universal rest and increase of entropy, the consequences of the recently discovered second law of thermodynamics. This was quite as serious a concern in the 1860s as global warming is today. Darwin, I hadn't noticed this quote till recently, Darwin said that Thomson's view of the age of the Earth is one of the world's sorest problems. This theory was eventually proved, fortunately, to be wrong, because it did not include the enormous thermal energy that will be released into the universe initially, to some extent, by radioactive decay discovered by Becquerel and the Curies around 1900, and then to a much greater energy by nuclear fusion, which will keep the sun going for several billion years more, as discovered and proved by hydrogen bombs and in the labs in the mid-1990s. Some novelists use conversations as a very effective way of introducing scientific ideas into their novels. In Our Mutual Friend, again, the gaffer's children, Lizzie and Charlie, sit in their riverside house looking at the burning coal in the grate, waiting for their father to come home, who was working on the river. Then, quote, then as I sit a-looking at the fire, I seem to see in the burning coal, like where that glow is now. It comes like pictures to me, Charlie. That's gas, that is, said the boy, coming out of a bit of a forest that's been under the mud that was under the water in the days of Noah's Ark. Look here, when I take a poker and give it a dig. So after being asked to think in this book earlier about the mysterious future of the sun, and here the reader is taken on an imaginary journey back through time to some prehistoric era, of which many of Dickens' readers would have heard about in their recent debates about evolution and the age of the Earth. In the scenes on the Thames, part of this book, an old man is being rowed by his young daughter in a small boat among the barges and sailing ships. She is horrified as he collects floating bodies for the sake of a few coins in their pockets. The description of the watery environment on which their livelihoods depend is focused on the ripples, waves, and eddies produced by boats and currents. Actually, Dickens had written, he was a great fluid dynamicist, Dickens, that's perhaps why I'm speaking here today. Dickens had written about his fascination with water ripples and boats in his diary of his American journey in the early 1850s. When he travelled for 2 days, we toiled up this foul stream, which is how he referred to the Mississippi, striking constantly against the floating timber. When the nights are very dark, the lookout in the head of the boat knows by the ripples on the water if any great impediment be near at hand, and rings a bell beside him, which is the signal for the engine to be stopped. It's no easy matter to remain in bed. So these were the sort of dramatic ripples and rivers that he was interested in. Back to mutual friend. One evening, the father is out on the Thames. So we're now reaching the great scientific point of this lecture, by the way. The father is out on the Thames and on his own boat, and his own boat fails to return. The drama later then moves to the water's edge, where the waiting of the family group becomes ominous. As elsewhere in his novel, the protagonists are carefully observing their surroundings. At this time of their watch, the water close to them would often be agitated by some impulsion given it from a distance. Often they believed this beat and plash to be the boat they lay in wait for, running in ashore. And again they would have started up, but for the immobility with which the informer, well used to the river, kept quiet in his place. Now, you might not think this was a fantastic moment of science, but when I read this, I was astonished. Because this is a significant statement in 1865 in which you could say that art is benefiting from science. A new concept has been introduced about the way that a boat produces a confined motion of a water surface which travels over an appreciable distance. This motion, which could be an eddy or a vortex or a wave, has an impulsion, normally in physics referred to as an impulse. This means that the motion produces a force on the water and a force on another boat, if it's in the surroundings, and will create a disturbance when it reaches the shore. In fluid dynamics and mathematics, this is a subtle and complex idea, still being studied today in different situations. Because although a vortex or a wave produces motions over a wide area and in different directions, there is overall a net forward force. Dickens cannot have got this idea. The question is, where did Dickens get this idea from? He cannot have got it from those scientific papers on the subject because they were written later. There was an early work on vortices, but the idea of connecting vortices to force came with the work of a German, Gustav Kirchhoff, in 1869, 4 years later. And Kirchhoff was obviously not influenced by Dickens, most unlikely. So one can think in this example, I should also then say that the conclusion of this idea was then well established mathematically by Kirchhoff. It was then taken up by Kelvin. And in fact, this impulse of a vortex is referred to as Kelvin's impulse. That's another example, I'm afraid, of the Brits taking a German name and giving it a British name, but never mind. One can think of examples where art foretells advances in science and technology, such as the planets of Mars suggested by Swift in Gulliver's Travels, or Jules Verne's travel in Rocket in Space. So this was an example, perhaps, of that sort. But I don't think it was, because I think Dickens, in fact, got this idea from a colleague who was John Scott Russell, who's the sort of the hero of this lecture, who was a railway and ship engineer who worked as the railways editor for Dickens in the Fleet Street office of his newspaper, Daily News. This is another of Dickens's publication projects in about 1849. Scott Russell was a graduate of Glasgow and St Andrews Universities, where he'd done some teaching and construction of steam-driven road carriages, one of which sadly crashed with fatal results. Perhaps that was the reason he moved to London. That's not stated. He moved to London in the 1840s. In his ship designs, he was the first scientist to identify how waves created by the ship had a force associated with them. He had an earlier experience and interest in waves, in fact, back in Scotland, when he was walking along a towpath, and sometimes you may have done this yourselves, and a ship moves, it can produce a wave that can travel along the canal. And Russell described this as a solitary wave, or a little mountain of water that moves under its own dynamics. And in a famous experiment, which he reported to the British Association in 1845, he measured the speed by galloping at about 15 miles per hour along the towpath of the canal to verify how it moved. The constant behaviour of this moving wave was quite different to the earlier ideas of waves by Stokes, and it was proved by later papers by Lord Rayleigh here in London and Boussinesq. You'll see fluid dynamicists do enter the House of Lords from time to time. This is part of the British Constitution. He then applied this observation to the design of steel ships. He was involved with Isambard Brunel in the construction of the Great Eastern, which is this great iron ship launched down near Millwall, launched sideways into the Thames, and then it sailed across the Atlantic in 1858. He explained to the Royal Institution the principles of this in 1848, with the Duke of Northumberland in the chair, as the minutes of this lecture say. And the lecture was on the wave principle applied to the construction of ships. He explained that the amount of moving power required to move a vessel will vary with the bulk of the water disturbed either side of the bows of the ship. And, he comments interestingly, this volume is less than the immersed volume portion of the vessel. These ideas led to the sharper bows of clipper sailing ships, which considerably speeded up shipping. It seems very likely that Dickens would have heard all about this from Russell, since they shared the same office of the Daily News. And he might have remembered this when he was writing Our Mutual Friend 15 years later. But I could find no proof. There is no correspondence between Dickens and Russell on this topic. The biographer of Russell makes no reference to conversations with Dickens. So there's a literary whodunit for somebody to solve. Returning, if I may, to the expectant party on the river, as they counted the hours and looked at these eddies, they made a further interesting observation, which again many people don't know even today. The wind carried away the striking of the great multitude of the city church clocks, for those lay to leeward of them. But there were bells to the windward that told them of its being 1, 2, 3. So he's telling the readers this great discovery that was made in the 1850s, John Tyndall and Stokes, that although sound travels quite fast, about 300 meters a second, actually if the sound is downwind, you can't hear it. The reason being that, as we now know, the sound goes up into the atmosphere above you, and that's why you can't hear it. If you're on a very tall block of flats, you can in fact hear the sound downwind. So this was another sort of scientific, a very important and interesting scientific discovery of the period that he put into the book. In fact, the question of sound waves and the acoustical design of large buildings and concert halls was the subject of another of Scott Russell's lectures at the Royal Institution. Finally, scientists, engineers, and society, if I could summarize. Dickens' thoughtful writing about science and its contributions to his novels is consistent with his affirmation in the last decade of his life about the broadly beneficial effects of science and technology on the nation and on people's lives. Peter Ackroyd's biography explains that despite Dickens' reservations about the nationalistic tenor of the Great Exhibition of 1851, at the very end of his life, he was praising, this is a quote from Ackroyd, at the very end of his life, he was praising the major discoveries and inventions of his period that romantic idealists like Ruskin and Morris disparaged. I would agree, this is J. Hunt speaking, I would agree with Ackroyd's conclusion that in that sense Dickens was very much a modern man, very much a man of his period, and highly sceptical about, quotes, the good old days. Dickens' journalistic colleague, Scott Russell, showed the excitement and practical importance of applying science and engineering, and he was a member of the Royal, of the Commission, the commission which founded the Royal Exhibition. And Scott Russell was very interested, as I say, in applied science and engineering, but he was also concerned about that British business should make every effort to make commercial use of these developments. Russell and others involved in holding the Great Exhibition in 1851 expressed their concern that companies in the United States and Germany were already overtaking British business for three main reasons. They were using British inventions such as the wave-line design of ocean and river steamers. They were employing more highly educated staff. They also had a prejudice in favour of novelty. Do those ideas seem a bit frequent? Anyway, this is how Russell explained it in the Royal Institution. Scientists can certainly learn something, even today, from Dickens' summary of the three stages in the development of ologies. Most accounts of science, I believe, focus on stage one, data, ideas, and the corrections, which does not mean rejection, of course, as Popper and Lakatos have forcefully explained. Stage 2 involves explaining and popularizing the utilitarian, inspirational, and aesthetic aspects. All aspects are important. And I suspect research councils might call this impact. But scientists should simplify and summarize for their own benefit in order to move on to the next step in their science, as Poincaré explained. But Dickens' stage 3 is not generally discussed. That is the importance of generalizing ideas from one branch of science to another. And this is not generally thought of as part of the job of a scientist. It's a pity, because people do not appreciate what pleasure and interest this aspect has in discussions with other scientists and in quiet contemplation, as George Eliot reminds us. An increasing number of popular books, however, having addressed this aspect of science. For example, Gleick's wrote about the widespread application of the ideas of chaos theory or evolution of systems. Cross-disciplinarity is essential for tackling great problems of our times, but many scientists regard this approach with considerable suspicion, as one has seen recently when economists or political scientists receive suggestions from scientists working in engineering or biological systems. Perhaps we need more Pickwickian brainstorming meetings on Hampstead Heath. Thank you very much.